So we're going to derive the moment of inertia for a thick ring. All right, let's start with, I guess I'll just, read out what it is that we have to do, because there's a bit of a procedure, but there's some stuff about it that is kind of, takes a bit of a challenge. I'm going to start by identifying a piece of the ring itself. And again, it doesn't matter how much extension there is behind this. We're assuming that the thick ring can be either an area or a volume. I'm going to treat it as an area, so I think that'll work out just fine, okay? I'm going to choose a part of it somewhere in the middle, and I'm just going to say this is our mass, so this is dm. And I want to find a way to point to one of the corners of this piece of mass. So as before, I will kind of start with this being 0 and use a placeholder for the angle to indicate I have to go out some angle and out some distance. I'll use a placeholder for the distance. And I think that I can identify every piece of the mass by using a theta and an r to designate where each piece might be. I'm going to need to have some other placeholders. So I'm going to do Ri for the inner radius and Ro for the outer radius. And I'm going to say that the entire thick ring has a mass of m. Since I'm going to be looking at the ratio of the mass to the area, I'll need to come up with an expression of the area of the thick ring. So I think the best way to do that would be the area of the big circle minus the area of the whole. This would give us the area of the whole thing. So pi r outer squared minus pi r inner squared will be the whole area. Does that make sense? All right. Put that over there. Okay, so I guess my next step is to try and define the area in terms of the pointer variables, because I've identified that this is an area, and I want to be able to point to each piece of area, but I want to do so by using r and theta. So I want to define the area in terms of r and theta. We've done this a couple times before, but I'm still going to try and do it again by having us recognize that this portion here would be r d theta, and this portion here is dr, and that would make a r d theta times dr. Everything okay there? No one's saying anything, so I'll just assume yes. So with that, I'm going to try and find a way of writing dm in terms of the area. So dm is to dA as the entire mass is to A, which means dm equals m over A dA. And for the time being, just so it's not so cumbersome, I'm just going to leave A in there, and then I'll plug that whole pi r squared minus pi r squared thing in later. But I will have to replace dA with r d theta dr. So dm equals m over A r d theta dr. All right, I think I've done all the major heavy lifting now. I have an expression for moment of inertia. I'm going to use the expression and do some substitution. So my expression for moment of inertia is the integral of r squared dm. Now, r represents the perpendicular distance from the axis of rotation to my piece of mass. And I think I can just leave it r, because this looks like the perpendicular distance from the center of rotation to where that piece of mass starts. So I think we're still within that definition. So I will rewrite this as the integral of r squared, but I'll replace dm with m over a r d theta dr. Now doing that adds another derivative variable, so I need to add another integral variable here. And I want to set my ranges. So I'm going to go for every theta because I'm going all the way around the ring. So I will go from 0 to 2 pi for theta. But for r, I'm just going to start at r inner and go to r outer. All right? Any questions about any of those choices I've made so far? All right. I'm going to reorganize a little bit. I'm going to also state for kind of the record that r and theta are not directly related. For every theta, I'm going to have the same range of r. So I don't have to worry about, is there an expression to describe the limits of r based on theta, meaning every single angle that I choose, I'm going to start at r inner and go to r outer. Does that make sense? So I can separate these integrals. And that'll be true for all the ones we ever do. So I'm going to pull out the constant, and I'll have from 0 to 2 pi d theta, and from r inner to r outer, r cubed dr. This should give me my moment of inertia of my ring. Any questions about any of those choices? Okay. So I'm not left with very much to do except some quick work. The antiderivative of d theta is just theta. So this will be theta evaluated from 0 to 2 pi. And the antiderivative of r cubed, well, I'll add 1 to the 3 and get 4. And I'll divide by my new exponent, so it's 4. So this will be 1/4 r to the 4th evaluated from r inner to r outer. All good there? All righty. This is still m over a times 2 pi times r outer to the 4th divided by 4 minus r inner to the 4th divided by 4. I can do a little bit of factoring. I could factor out the 1 over 4. You can factor out the 2 pi, and the 2 and the 4 will cancel, and this will give me m times pi divided by 2a. But instead of a, I'm going to go ahead and put this as r outer to the 4th minus r inner to the 4th. And I'm going to sub in what I know about a, which is pi r outer squared minus pi r inner squared. Okay, I did a couple things at once there. Am I clear for that? Or do you guys need to look it through? To me, there's absolutely nothing wrong with this being a viable derivation and test question. They've never asked it before, but I just don't see anything that's terrible about it. So I can simplify this. There's a pi in the numerator and a pi in the denominator, so I'm going to get rid of those first because there's 1 in both of those terms. And this is where knowing a little bit about factoring can help you out. The top is a binomial, the difference of squares. It's a difference of squares. The bottom is also the difference of squares, but the difference of squares on top that I think is going to help me. First, I want to state that r outer can't equal r inner, or else I get a 0 in the denominator. Well, it wouldn't be a thick ring then. So I'm just making sure we understand that those have to be different. And I'm going to go ahead and use the difference of squares formula, which is r outer squared minus r inner squared times r outer squared plus r inner squared. That's the factoring for the difference of squares. And on the bottom, I'll just have r outer squared minus r inner squared. Kind of saw this, that because I had them to the fourth, that I could do this factoring. And if I do this factoring, it'll cancel out the one in the denominator. So that's what I'm going to do here. I'm going to cancel this with this. And that'll simplify this a lot. 1/2 m r outer squared plus r inner squared. I always thought that this particular moment of inertia looked weird because it had the sum of the two radii, but it's just a factor of the way the area works out that makes it look like this. So, there we go. Now we know that if we are launched at 10 meters per second, we make it to the ramp, and the ramp doesn't move, we make it all the way to the top of the ramp, we will be traveling at 7.6 meters per second off the top of the ramp. I don't really need any of this other work anymore. I just needed that to get me to the top of the ramp. So if there's no questions about that, we'll go on to question C. All righty. So I don't need this. Let's erase it all. Bye-bye. You are unnecessary. This is a projectile motion problem. There's not a whole lot I can do to speed this part up. The object's going to travel in a parabolic path. There's no shortcut here. The only thing I can do is figure out how long the object is in the air and then use that to figure out the horizontal displacement along the ground. So I'm going to do our old school thing from way back in the day, horizontal, vertical, and, well, I guess we used to do it the other way. Vertical, horizontal, there. So the range, Vx is going to be 7.6 cosine 25 degrees t. Delta y is going to be -3 meters. Vy naught is going to be 7.6 sine 25. I don't care what the final velocity is. I'm interested in finding how long it is in the air. So -10 meters per second squared. And I just need to find the time. So I'm going to ask a random person in the room in 60 seconds how long it's in the air. Okay. So 1.15 seconds, that's going to be in both places. So my horizontal range will be 7.6 cosine 25 times 1.15. That's where it lands. That's what this problem is looking for. This is a real FRQ. It was on the exam years ago. This is very, I don't know, what would you use? There's a lot of just mathing the whole thing out, but this will be where it lands. So I got 7.9 meters away from the edge of the ramp. Hopefully you guys got something similar. But yeah, neglecting air resistance, calculate the horizontal distance. So I think a lot of people think that the ball is going just horizontally off the ramp, but it's going to go at whatever the angle of the ramp was. So this makes this a full projectile problem. Suppose instead that the sphere were to roll towards the incline as stated above, but the incline were frictionless. State whether the speed of the sphere just as it leaves the top of the incline would be less than, equal to, or greater than the speed calculated in B. It'd be less. It's still spinning. So it didn't convert that rotational kinetic energy into translational kinetic energy. So it's going to be going slower.
Wait, can you say the reason?
Yes, because it's still spinning. It never converted any of the rotational kinetic energy into translational kinetic energy. So all that energy is still the same. The rotational energy is still the same. Or if you'd like, say it couldn't use any rotational kinetic energy to get itself up the ramp. It had to use just translational kinetic energy. So its linear speed will be less because the linear speed will be unaffected by the rotational kinetic energy. Any number of things you could have said there would have been fine. All right. So let's start with, we have two small spheres of mass m. separated by what they characterize as a large distance. So that's fine. Well, not like that. That. And there's a thin rod between them. Something like that. And a bug conveniently lands over here. And the bug has mass 3m, and each of the spheres is mass m. And the whole thing is mounted in such a way that it can rotate about its center. Question A. Determine the torque about the axis immediately after the bug lands on the sphere. Well, I think there are two torques about the axis. There's a torque due to the force mg acting on the right side, and it's acting, of course, downwards. And there's a torque due to the 4mg acting on the other side. And the rod itself doesn't apply a torque because it's thin. It's a thin rod. But more importantly, it's mounted at its center, so I only have to worry about these point masses that are on the ends. This length is L, so if I'm just going to make this convenient for me, I'm going to say a rotation out of the board is positive. So I have two torques, but the net torque is going to equal I alpha. So I think I'll work on the torque portion first, and then I'll work on the moment of inertia part second. For the torque, I have the torque on the bug side and the torque on the sphere side. The bug side is going to be a positive torque, and the sphere side is going to be a negative torque. R cross F makes the bug's torque out of the board, and R cross F makes the sphere side a negative torque. So the first torque will be L times 4mg times the sine of 90. The second torque will be L times mg times sine of 90. So that's clearly 3lmg, right? When I add those up. All right, let's do the moment of inertia now. I have 2 point masses, one on each side, both the distance L away. So the point mass for the bug and the point mass for the sphere. I'm just going to use the point mass formula. That'll be 4mL squared, bug side, and just mL squared, sphere side. These just add together to give me a total of 5mL squared for the total moment of inertia of the system. So 5mL squared times alpha. So question A, determine the torque about the axis immediately after the bug lands on the sphere. Oh, I didn't have to do this? So the torque is this. Determine the acceleration immediately after the bug lands. Okay, that's what we're doing now. Solve for alpha. M cancels, one of the L's cancels, and I'm left with alpha equaling 3g over L. Units work out? Yeah. G is meters per second squared. And L is in meters, so I just get radians per second squared. That's what I'd expect alpha to be in, so it looks good to me. Except I forgot the 5, so I'll put the 5 there. Okay. Alrighty, that was it. A and B. Thank you. You're welcome. I'm sure question C is how fast is it going when the bug is at the bottom? And you can't use easily the acceleration here because the acceleration isn't going to stay this. The moment it starts to move, the acceleration becomes less because the angle of the force relative to the torque arm is changing. So in fact, when it's at the very bottom, the torque is 0 because the force is straight down and so is the torque arm. So the angle ends up being 180 degrees and you get a sine that's 0. So there's probably a better way to find the speed at the bottom. I don't think you can do anything about momentum either. But I do think you could probably use conservation of energy to figure out how fast the system is spinning at the bottom. The only thing is, if you're going to use conservation of energy for that, you don't need any of this. So just get all this out of the way. So this represents the initial state of the system. And the system is going to rotate. So let's consider the final state of the system. If I can, give me a second. There we go. So the final state of the system will look like that. It looks like this mass lost gravitational potential energy. It is now lower than it was before. This mass was lifted upwards. It is now higher than it was before. But both of these masses acquired kinetic energy. Right, Olivia? Did you figure out how fast it's going? Excellent. So that's how I'd figure out the speed of the bug at the bottom. But we would probably do that in terms of an angular speed. I'm not sure. You could do it either way. You could do it as a linear speed. They're point masses. Whatever would work best. We know that whatever velocity we have here has got to be the same as the velocity here. So you could do this in terms of the linear velocity or the angular velocity would be fine. Since you already know the moment of inertia, angular velocity will probably be faster. But you're going to need the linear, well, you don't need the linear velocity to do the next part. Because once we do that, find the angular momentum is just multiplying I times omega. And then E, net force equals MAC for the bug. And since you can express that in either omega or V, whatever one you want to use. So that's kind of how C, D, and E will come together. I mean, we could perform it if you want, or if that's enough, and we could leave it there. Okay. Kendall? Yeah. Sure. There's two ways that I can present that, and one of the ways might be new to you. So when I say new, what I mean is I can treat each sphere's point of reference separately, but that confuses some students. So, but that's what I would do. So what I mean by that is I can say that this object has no potential energy at the start of the problem and has potential energy when it's here, but that this one has potential energy at the start of the problem and has no potential energy here. Some students don't like that because they're saying, well, if you're making this the reference level, doesn't this one have potential energy at the start of the problem? And what I'm saying is that, well, it's a relative value. This is the lowest point that this mass ever makes it to, so that's 0 for that mass. But I did say in class that you pick a uniform reference level and you do all of your measurements from there. It won't make any difference to the answer. So because I'm afraid that if I do it the other way, it'll confuse you, I'm going to make the bottom the universal reference level. And I'm going to compare the two states. So that means that this mass starts with a gravitational potential energy, mgl, and the other mass starts with a potential energy of 4mgl. And then after they've rotated 90 degrees, the one mass has potential energy mg times 2l, and then there's some kinetic energy. Now we can decide how we want to deal with the kinetic energy in a minute, but that's going to be how we work it out. Now, it should be clear that the mgl part just gets added to both sides, so it goes away. But if I want to find the kinetic energy will be 4mgl plus mgl will be 5mgl minus 2mgl will be 3mgl. This one isn't. This one's rotating to here. So it starts with gravitational potential energy. It's above the baseline.
Then why is the NG2O on the other side of the equation?
Because that one started at a height L and ended at a height 2L. right? Yes, Kendall?
Sure.
Look, I would set this equal to 1/2 I omega squared, since we already found out what the moment of inertia is. This would give us a way to get the angular speed. Now, we don't have to do angular speed. You could have done linear speed, but this would give us the angular speed of the system. Once we have that, I times omega is the answer to D. And then I would use net force on the bug equals 3m omega squared times L. I would replace AC with omega squared L. And since we have omega already here, it's a pretty straightforward substitution. All right, so I have a ramp that is inclined 25 degrees and has a max height of 3 meters. A sphere, solid sphere, is rolling at linear speed of 10 meters per second. And the sphere is going to make it to the top of the ramp. The question asks, how fast is it going at the top of the ramp? Well, the direction's easy. It's going to be going in whatever direction the ramp is, so 25 degrees. Speed, well, let's at least consider that there's the possibility it doesn't make it to the top of the ramp. So that is plausible. I think if we try to find a velocity and find some weird, discrepant answer, like square root of a negative sign or something, that perhaps it doesn't have enough energy to make it to the top of the ramp, but I think it probably does, or they wouldn't ask about it. So, and they're asking for the velocity at the top of the ramp. That suggests it still has kinetic energy at the top of the ramp. So with that kind of a set of assumptions, I'd start with 1/2 mv squared plus 1/2 I omega squared at the bottom of the ramp. Has to equal mgh, because it's clearly above the reference level, plus 1/2 mv final squared plus 1/2 I omega final squared. Still rolling. And this is all at the top of the ramp. We all good? All right. They say it's rolling, and they tell me it's a sphere. There's a lot of things I can do right away to make this work out easier. So let's consider doing them. 1/2 mv squared plus 1/2 times 2/5 m r squared times v over r squared. All right, this is going to get rid of the r's, put everything in terms of v. I'll do the same thing on the other side. So I have 1/2 mv squared plus 1/2 times 2/5 m r squared times v over r squared. I'm putting little f's here to make sure this is the final velocity versus the initial velocity. The 1/2s cancel, the r's cancel, and that gives me 1/5. And 1/5 and 1/2, common denominators of 10, 7/10. So 7/10 mv squared equals mgh plus 7/10 mv final squared. No reason to redo the math, it's all the same math. M's all cancel, or they can be factored out and removed. So I'll get 7/10 times 10 squared equals 10 times 3 plus 7/10 V final squared. All right. 10 squared is 100, divided by 10 is 10, times 7 is 70, so 70 minus 30, all times 10 sevenths equals VF squared. So that's 400, root of 400 sevenths. That's got to be how fast it's going at the top. I have the magic adding box. Still think I'm working a lot harder than I should. 7.6 meters per second is how fast it leaves top of the ramp. All right. Was that all you wanted? Or do you need more than that? How long is it in the air for?
Move a little back up. I was confused with what you did to remove the omegas.
I subbed in V over R. It's rolling. Right, and V equals omega times R is the condition for rolling. So I'm just talking about doing this and subbing that in for omega. Good? Yeah.
So the bottom problems, that's projectile motion.
Sure are. Well, C is.
Yeah, I was wondering, because I just solved it like these two, but I was wondering if it's different because it's also rolling.
Once it goes into the air, it's no longer rolling.
Okay, so it's
Right.
the same.
Yeah, it's just a projectile. So just launching at 25 degrees. You got to do it the long way. There's no other way to do it, really. So you got to find out how long it's in the air. I think it's in the air for 1.15 seconds. And then you can use the horizontal velocity to figure out where it strikes the ground.
Okay.
So there's not really a shortcut there. Sorry. You know, you're kind of stuck with the old, either the quadratic formula or plugging it into Desmos or something like that. You'll have Desmos in the exam, so I get used to using it. So not a problem. I'm going to just draw a triangle. Not because this is the shape of the object. I don't know what the object looks like and don't have to. I just want something that I know clearly looks as though it's heavier on one end than the other. Is that all right? Because that's what this says. It says that the density is C times X. And density is the ratio of the mass per unit length. The problem is that the ratio of the mass per unit length is different from the light end to the heavy end. Now, question number 1, asking about the mass, it's kind of optional. You have to find it anyways to get the second answer. So if you didn't know that, then you might have gotten, well, maybe more stuck than you were. So asking for you to find what the mass is in terms of the variables is prompting you, because your definition for center of mass is the sum of x dm divided by the entire mass. So you have to have the entire mass, one way or the other, in order to get the second answer. I'm just throwing that out there because you don't have to ask for it, knowing that you would have to do it anyways. So I think this is a nice prompt to let you know you're going to have to figure out what the entire mass is first. So let's do the problem in order. I want to start by saying that the ratio of dm to dx has to equal lambda. That's the definition of density, the ratio of the mass per unit length. So once I have that ratio, I can solve this for dm and make note that if I take the integral of both sides over the entire object, this should give me the total mass. I'm summing dm. That should give me the whole mass, right? I'm going to sum for every piece of mass. Now I can't do this because lambda is related to x, so I have to substitute in my relationship for lambda because it's in terms of x, meaning this piece of mass is a different density than this piece of mass, but we're adding up all of the pieces. So I want to rewrite this as lambda cx dx, and I want to add from the first piece of mass to the last piece of mass. Does that make sense? Any questions about what I put there? Well, this should give me the entire mass. C is a constant. I can take that out front if you care, leaving me with just a very straightforward integral. So this is a polynomial, x to the 1 power. I will add 1 to the exponent, divide by the new exponent, and get c times 1/2 x squared evaluated from 0 to L. Any questions? So my mass is going to be CL squared over 2, just like it says on the tin. Good to move on? Alrighty. Well, I'm going to choose this to be my point of reference because it said from the light end, and this is the light N. I'm going to point to that piece of mass using a placeholder x, because it is a distance x away. And my definition of x center of mass is the integral of x dm divided by the entire mass. Okay? Well, let's see. I'm just going to do the top part first, but I already have what I want to use for dm. From this point forward, dm is just going to be cx dx, right? I'm not going to put in lambda every single time. I'm just going to put in cx for lambda. That okay with you guys? You guys good? All right. So x times dx, which is cx dm, evaluated from 0 to L. I'm just going to do the top part of this fraction, then I'll divide by the mass at the end. Is everybody okay with that? All right. Factor out the c, and I'm left with x squared. I know I wrote dm there, but that's just a mistake. I should have written dx there. dm equals cx dx. So I just made a faux pas. Let me fix that. That okay? All right. X squared, just a polynomial. Add 1 to the polynomial and divide by the new, add 1 to the exponent, divide by the new exponent. Evaluate from 0 to L. This looks to be CL cubed over 3. Now, I wanted the center of mass. This is not the center of mass. This is just the top portion of the fraction. I have to divide by the mass of the object to get the actual center of mass. I'll remind you, x center of mass is that integral, which is CL cubed over 3, divided by the actual mass, which is CL squared over 2. Seems to me the C's cancel out, and then 2 of the L's cancel out, and I can bump that 2 up to the very top, right? Just multiply top and bottom of my fraction by 2, and that whole thing becomes 2/3 L. We all good with the algebra there? Hope so. But all right. Kind of knew that going in though, didn't we? So, I mean, they gave us all the answers. That's not accidental. A lot of the exams will do that now. They'll give you what you're deriving. They won't give you a point for the actual answer, but that way you can do the rest of the question if you need that answer. Does that make sense? All right. Alrighty, one more thing to do. Moment of inertia is defined as the integral of r squared dm, where r represents the perpendicular distance from the axis of rotation to each piece of mass. Pretty sure in this problem that perpendicular distance is x, right? So it's linear, it's got linear symmetry. So my integral, x squared, I'll replace dm with cx dx from 0 to L. And we're just doing the same thing over and over again. I'll factor out the c, integrate from 0 to L, x cubed dx. Polynomial, so that's going to be 1/4 x to the 4th evaluated from 0 to L. that will just be CL to the fourth over 4. I don't really like this answer. I know it's in terms of C, and this is probably what we're supposed to do, but we have no real way of comparing this to like a regular rod. We know that a rod about its end is 1/3 ml squared. I'd expect this to have a higher moment of inertia because the center of mass is further away. The heavier parts are further away than if it was a uniform rod. It'd be nice if this was in terms of the mass, then we could make a clear comparison. So let's make a clear comparison because we know the mass is CL squared over 2, right? So let's go over here and factor out CL squared over 2, which is going to leave me L squared over 2, right? I'm just factoring it out of the moment of inertia. If I do that, I know that CL squared over 2 is M. If I just rewrite this a little bit, I get 1/2 ML squared. Well, that makes sense. 1/2 is bigger than 1/3. So this is more difficult to turn. It has a higher moment of inertia than if it was a standard uniform rod. Does that make sense? Now, this is the answer they were looking for here. But I just wanted to make sure we took a moment and said, well, how does it compare to a rod if it wasn't heavier at one end than the other? Well, that's how. All right. So, I don't think I'm going to need all of these things that are here, but let's go ahead and read the next part. What will be the angular speed of the rod when it swings to its lowest position? When A, the light end is affixed to pivot, and B, the heavy end is affixed to the pivot. Be aware you may have to use the parallel axis theorem to find a moment of inertia about the heavy end. Actually, I think we shouldn't use the parallel axis theorem. And I want you to think about maybe why. I think we should derive it and then use the parallel axis theorem to see if the parallel axis theorem works for something that has a non-uniform mass density. Also consider we don't have the moment of inertia about the center of mass, we have the moment of inertia about the end. We're moving it about the other end, which would mean at minimum we'd have to use the parallel axis theorem twice. Once to shift it to the center of mass, then once to shift it from the center of mass to the other end. Things to keep in mind. It just might be faster to just redo it from the other end. But here we go. I don't need all this stuff that's here. So I think we can get rid of all of that. Well, I don't want to get rid of all of that. Just some of it. There. All right, so we found that the center of mass is located 2/3 of the length. So if we're going to pivot this about here, the center of mass is here. So this object is going to swing downwards. So I'm going to have the condition where the object is like that. Right, it swings downwards. So I believe the object begins with gravitational potential energy and ends with rotational kinetic energy. And I'm going to assume that this represents the baseline level for the object. So my height's going to be measured relative to the center of mass. Center of mass is 2/3 L. So that means that my gravitational potential energy is mg times 2/3 L. That's how high it is above the reference level. This is going to equal 1/2 I omega squared. So that's about it. We know that I is CL to the fourth over 4. So 1/2 times CL to the fourth over 4 omega squared equals M, which is CL squared over 2 times G times 2/3 L. Don't make the mistake and not cancel out M, right? M is an expression. So we need to put that expression in. All good? Alrighty. I just got to clean this up and solve for omega. So I get rid of the c's. I get rid of a lot of the l's. I have an L cubed on one side and L, maybe for you guys, I should probably, I don't know, do an intermediate step. So L to the fourth omega squared over 4 equals 2L cubed G over 3. Intermediate step. So I can't see much else. I'm going to have 8G over 3L equals omega squared. I think my algebra is good there. You guys are good at algebra. Did I do okay? So take the root. G is in meters per second squared. L is in meters. So that gives me nothings per second squared. Take the root, that's nothings per second. So I get answers consistent with omega, which would be radians per second. So it's one way to check on my, my math. Alrighty. We know the moment of inertia about the side. Let's see what the parallel axis theorem gives us and see if what we get for the parallel axis theorem makes sense. If we don't buy into it, we can always prove it. The only problem is that calculating the moment of inertia about another location, we don't have the density in terms of that. We have the density in terms of starting at 0 and going towards the heavy end. We would have to rework the expression for the density starting from the heavy end to go towards the light end. You follow what I mean? So x at 0 would be the heavy end, and x at all the way to the other end would be 0, or the mass would be 0. Okay, so, but let's work this out. The moment of inertia about this end, as we already know, is CL to the fourth over 4. That equals I, center of mass, plus mx squared. So x was the shift distance, and the shift distance is 2/3 L, right? It was shifted from the center of mass to here. So I want to find I about the center of mass. I would write CL to the fourth over 4 equals I, center of mass, plus m times 2/3 L squared. This is how I will shift the center of mass back to, shift the moment of inertia back to the center of mass. M, though, you know I'm going to have to put in our expression for m here, right? So let's not forget, m is CL squared over 2. There we go. All righty. Now everything's in the right terms. So this is still CL to the fourth over 4 minus 2's cancel with one of the 2's, and I get 2/9 2CL to the fourth over 9. Somebody check my algebra, because I don't know. I'm getting a little punchy here at the end of the day. I've been doing a lot of the algebra. I'm good? Algebra just fine? Common denominators there, 36. Can't think of anything else. So 9 minus 8 is 1. Is that right? Perky. So 4 goes into 36, 9 goes into 36, 4 times 2 is 8. So I'm thinking this is just CL to the fourth. Okay. That's not the answer. That is the moment of inertia about the center of mass. And I will point out it is less than the moment of inertia before, right? That makes sense. I expect it to be. We are in the middle. And more of the mass is closer to our axis of rotation. So now let's move it 1/3 away from here to get it to the end. So I parallel equals CL to the fourth over 36 plus mx squared. You guys are making me do a lot of this work. You should do all of this. I shouldn't do any of it. I guess keep my brain nice and juicy here. CL squared over 2 times 1/3 L squared. Alrighty. 3 squared is 9, 18. So this will be 2/18, right? Or 2/36s? Somebody should check my math on that. What?
What's with the 1/3 L? I stopped following what you were doing.
Why? Is it because I'm boring? I am boring. This is
No,
mind-numbingly dull.
I just got lost at that point. I was following before that. But what's the 1/3
All right. I got the message. Mind-numbingly. Well, I can't even spell. Numbingly dull. All right. Yeah, this is monumentally dull. We used the moment of inertia to figure out this. We used the parallax theorem to figure out the moment of inertia there. But they want us to swing this about its end. So now that I found the center of mass there, I need to shift it to here. So I'm shifting it one more time. There was probably a shortcut to doing this. I don't know that there was, but there probably was. I don't know. You mathletes probably could have done this in your sleep, right? You guys win awards and do mathy things all the time. Me, I'm just old and dull. Mind-numbingly so. All right, so, anyways, is my algebra right? Right, it is? I did okay? So, 2 plus 1 is still 3. And 3 over 36 will be 12, so CL to the 4th over 12. My new moment of inertia? Yay, I'm so proud of myself. Okay, now I have the moment of inertia. I'll have mg, can't believe you're making me do all of this, equals 1/2 I CL to the 4th over 12 omega squared. But I can't use m. CL squared over 2g times 1/3 L equals, oh my God, mind-numbingly dull, 1/2 CL to the 4th over 12 omega squared. Now this is just algebra some more. 2, and got the g there, keep that in mind. L squared and an L cubed, so an L in the denominator, 12 going up top, cancel with the 4, cancel with the 3. So I think I'm going to have 4g over L. I am very confident in that. But you guys should be doing the heavy lifting, so check my work. Come on, you guys love to find it when I make a screw up. This could be your big chance.
You got that right.
You're just saying that. You have no idea. You stopped writing things down an hour ago. Like that. So, I don't really want to do any more physics. What's my time like? How many minutos do I have? 11 minutos. Got it. I speak absolutely no Spanish. Hey, donde está el baño? I am so impressed with all of you who speak a second language because A, I am terrible at it, and B, I'm no good at it. And it's going to stay that way for the rest of my existence. So you guys who speak another language, I am always super impressed. Learn while you're young. All right. So a bug comes and lands over here. Who's laughing at my bug? After how nice I've been to all of you recently, that ends today. No longer being nice to anybody. All it does is bring you pain. Listen out there, internet. Nothing but pain. All right. Starting position of our system. I'm going to do this different than I talked about it in the last class because I full on confused a kid there, and I'd call them out, but they will get so mad if I do. So they were just way confused. So that's the final state of the problem, correct? Now, look, I would not do it this way. I would start by saying this object has no gravitational potential energy but gains some, and this object has potential energy but then loses it all. Like, I don't have to have the same reference level for each mass, but that's been full-on confusing students. So I will downshift into U, and I'll choose that as the reference level for everything. Doesn't make me happy, but I'm doing it anyways. That means that at the start of this problem, I have 4mg times L worth of gravitational potential energy for that bug and the sphere. And I have mgl as a gravitational potential energy for that sphere, because they're both that far above the reference level. So that's the total energy of the system. After it's allowed to rotate, the system has some amount of kinetic energy, for sure. I can either decide to choose that as linear kinetic energy for each object and sum it, or I could do the rotational kinetic energy of the system. I'm going to do rotational kinetic energy of the system. But this guy gained energy because now he's twice as high as he was before. That's the system. Any questions? Excellent. So in doing this, I have 5 mgl on one side and mg times 2l on the other side. That's 3 mgl equals 1/2, moment of inertia. Let's see. I've got 4ml squared plus ml squared. That's got to be the moment of inertia of the system, right? 2 point masses, each a distance L away from the pivot point. One of them has a mass of 4m, one has a mass of m. You just add up moments of inertia. That sounds like 5ml squared right there. Times omega squared. The entire system will have that velocity. Bye-bye m, bye-bye one of the L's. I've got a 2 there, so this looks like 6g over 5L equals omega squared. Units work out. It's the same stuff we had just a minute ago. So omega is the root of all root of GL. That'll be in radians per second. So there, angular speed of the bug. So does your mumbo jumbo look like that mumbo jumbo? Your words, not mine? Well, there's no telling. Maybe you're right and I'm wrong. It's plausible. 4 plus 1 is 5, minus 2 is 3. You have to use it. You have to include it. You can't just throw it away because you don't like 2s. I get it. Those 2s bother me as well. 2, the number of couples. We hate couples. No one deserves to be happy. Please, give me a break. That's how fast the system's rotating, right? So net force, I don't like that color. Let's try a different color. Net force has to equal MAC on the bug. So the bug, which is here, oh, that one's terrible. Going in that direction. The bug has to hold on to the sphere. The sphere has a mass of m, the bug has a mass of 3m. So the net force on the bug equals 3 MAC. There are 2 forces acting on the bug. There's the force from his little buggy feet this way, which, what do you want to call it, tension? And then a force of gravity downwards, mg. Well, 3 mg. So if I want the force on the bug from his feet, I guess, it's going to have to be tension minus 3 mg equals 3m, we got to use that thing over there, omega squared times L, right? Omega squared R is the typical value. We use v squared over r or omega squared times r. I'm going to use omega squared times r. That makes the most sense. But the r in this case is the length of that point from the pivot point to the end of the rod, which was L. Any questions? Come on, follow along. Keep up. The old man can do it. The young people should be able to do it too. So this is going to be T minus 3 mg equals 3m omega squared, which is, well, 3m omega squared 6g over 5L times L. Wow, L's cancel. Way to go. 3mg plus, this looks like 3 times 6, 18, 18 fifths mg. So 33 fifths mg, right? 15 fifths plus 18 fifths would be 33 fifths mg.